Okay, we start up again. I gave you some more material here under OpenFoam material that I want to show you. Meshing in OpenFoam. Meshing in OpenFoam. So yeah, here is something that we are going to look at. I've stolen this one from Wolf Dynamics, and yeah, they have some nice animation here. So when you want to use OpenFoam here, say simulating such a mixing tank where you have some baffles, some paddles that rotates, this is not easy. Then you create sort of a circular area here and mesh around these baffles, and then you let this part of the mesh rotate. That means the rest of the mesh sort of has to be standing still, so they are sliding against each other. Tricky, but possible. What was the other one? Yeah, sort of the same. Here also you see parts of the steady mesh and part of the rotating mesh. And how to mesh such a problem, a little bit complex geometry, that is sort of what we are aiming at now. Where were we? No. Did I destroy it? Hey. Blackboard. Material, OpenFoam material, and here we are. Thank you. So, I mean, you have done this a little bit already with the block mesh. And first we're going to look at, I mean, how far can you push the block mesh concept. And when that one sort of stops working, we have to do something else. So that is what we are going to look into afterwards. What kind of cells should you use? Always, if possible, rectangular cells. That is most efficient, well organized, and it will be much faster when it comes to the numerics and more accurate. Sometimes when meshing the geometry gets complicated, we have to use different meshes. We can't use rectangles. And yes, it's actually possible to do it. It will take more CPU. But yeah, you can still get a good solution. So when you have complex geometries, life becomes messy. And what is a good mesh? Well, we have some criteria for a good mesh. When you run the check mesh, he sort of reports how well is your mesh, more or less. But we really don't have any good theory for it, for saying this is a really good mesh. Standard rule, it should be pleasing to the eye, nice and smooth. Okay, that's a good mesh. Pleasing to the eye. I'm not sure if these images are pleasing to the eye, but so 4 elements here. Sort of the most common mesh quality that we can put numbers on. So we have now already discussed the orthogonalities and the non-orthogonal corrector number to help that. Then we have something called skewness, we have aspect ratios, and we have smoothness. So 4 elements here you should be aware of. So here you have the non-orthogonal problem. two neighboring cells, and then the wall between them, it's not 90 degrees here. So yeah, it's non-orthogonal. And then the problem then will be that this gradient normal to the faces, well, he's going to be different than the alignment from center point to center point. Remember when we sort of rewrite our partial differential equations with, say, an algebraic form using control volume analysis here, we are looking at the fluxes perpendicular to all faces. So yeah, we need this direction, definitely. It's going to be essential when you are calculating, say, fluxes in and out of this small control volume. And yeah, here you sort of have to then pay attention to, you have some misalignment here with the direction from cell point to cell point. And it will add diffusion into your solution. It will be diffusive. What does that mean? Diffusive. A diffusion mechanism, he mixes things. Dissipation, he will destroy things. So diffusion, yeah, you will have a higher degree of mixing than you should have, unless you have accounted for it. Then you have the skewness. Again, it's due to that you don't have pure rectangular meshes. And looking at two neighbor cells, yes, we are having algebraic equation system. We are addressing the center point P here and the neighboring point N. They have to talk to each other. And yes, we are going to need the flux through this boundary between these two cells. And the flux will then be evaluated sort of in the center between, in the center of this line. And there you see, okay, we can find the direction here between these 2 points. But the normal direction for this line, yeah, well, it's more or less the same, a little bit different maybe. But my center point on this line doesn't lie on the center line from node center to node center. So I get a small delta here that has to be adjusted for. So this is skewness. And yeah, also adds diffusion into the problem. So we really don't like that. But we have remedies for it, so it's possible. Third thing, aspect ratio. Yeah, you can have cells looking like this. They can be sort of very elongated. Don't have to be cubes. But be aware, I mean here, if you have, say, the velocity in the horizontal direction, and say this one is close to a wall, then it makes sense. Okay, you have the main transport sort of straight through these elongated cells. Okay. If your main flow direction here was upwards, this is suicidal. Don't do it. Of course, then you have one small velocity in the center here to represent the entire cell. Of course, you can't really handle, say, change in the upward velocity here when you have such long cells like that. So yeah, you may use elongated cells, but know where to use them. Alongside walls, okay. In the streamwise direction, main streamwise direction, okay. But if you have a lot of action here going up and down on such a mesh, terrible. Not good. And then smoothness. We have discussed this also previously. You shouldn't have, say, a delta change from one cell to the next larger than, say, 20%. That's the recommendation. In the old days we said 15%. So this then is not good. You have a big delta Y here, and then all of a sudden the neighbor is a very small one. Not so good. Much better to have it smooth and nice. Now we had a remedy, if you can recall, that was you could resolve the boundary layer with one command. Then you actually got something like this, and that's not good. It works, but you should be careful with it. Much better to have a smooth stretching of the mesh. Much better. So these 4 parameters, sort of something you have to think about. And also here, when you have different elements type, say you have a solid wall and then the flow goes horizontally here, nice velocity profile. And yeah, we are going to need the value here on, say, the right face. And of course, here you will have direct transport. The value you have here will be transported here, no problem. But when you're using triangles, then you see you will have some nasty side effects there. So it's just geometry, you might say. So the variable, generic variable phi, at the point f here, well, here you just say it will be the same as the one that we have here. It's just transported straight over. And you don't get any additional error terms. Here you have to adjust due to this inclination of your cell face. So triangles, yes, it will be more expensive than rectangles, of course. But I mean, sometimes you have no options, but just be aware, this costs more CPU. So here is a nice one. In the old days, in the 70s, if you use rectangular cells, you had a very good mesh. If you use triangle, oh, you had a very bad one. High error. But after the years has passed, we have been able to do better numerics, better interpolation. So now these two are quite close, actually. Of course, this one costs more CPU to handle, but you can get it almost just as accurate as with rectangles. So yeah, you're allowed to use rectangles. So simulating the flow around the London Bridge should be a piece of cake. Fairly heavy mesh, I would say. But yeah, if you have a problem like this, you have to have enough cells to cover the important physics. Yes, we know around a tower here you're going to have some vortex shedding, maybe a lot of action is going on. You have to resolve the boundary layer fairly good there. But say in the mean area here, where you have a big opening, yeah, you can have pretty big meshes. And also if you're interested in, say, what's the force on these towers? Then you're not so interested in what's going on all the way over here and all the way over there. You only look at the flow close to the important areas. So it's not necessarily the case then that more cells gives a better mesh. So be aware. As you now know, like with the Y plus problems for a turbulent case, then if you're using wall functions, then you have to use a coarse mesh close to the walls, or else you risk destroying the theory for using wall functions. Yeah, I think it says the same. Yeah, I have no time to go through everything of this, but yeah. Some word from the wise. Good mesh, not necessarily a recipe for success, but a bad mesh will guarantee you a bad solution. So avoid the GIGO syndrome, garbage in, garbage out. That's not a good one. So OpenFoam. Yeah, we have this, say, check mesh routine. He reports a lot of things, checks a lot of things. He has some default values, and they are hidden sort of somewhere inside something like this. And he will then give you maybe a warning and even an error if you violate these numbers. But I mean, you can change these numbers manually if you want. So that's actually an option for you. So yeah, I won't go through everything here in detail. So the guy who wrote this, Joel Guerrero, very experienced with OpenFoam. He has some personal values here that he uses. So maximum values for non-orthogonality, 80 degrees, and skewness, the number 8. So okay, that's something to learn from. But I think we had yeah, you have some options here. Also, if you have created a mesh and you get an error with, say, check mesh, your program may still run. Maybe the error is not fatal. And you can also have a look at the mesh even if he has check mesh has crashed or report some error. Then you may have to use this foam to VTK to create a graphical image that can be read in parafoam. Yeah, so it's possible actually to have a look at the mesh even though it has failed. And here also you can sort of check here, for instance, you have some points that are not in use in your mesh. And then you can actually visualize where are they to see what the heck is going on here. So definitely worth noticing here. Yes, it's possible to have a look at the mesh then, even though it sort of has failed or give a bad warning or something. Going through the details here a little bit, what he, the check mesh, what he reports. Then here, for instance, 16 unused points. Okay. Then maybe not crucial, but they shouldn't be there. So again, here he says failed. One mesh check has failed. Where has he failed? Well, here we have okay. Here is just dimensions, okay. Cell volumes is okay. This one is not okay. Mesh non-orthogonality, maximum 80, well actually 87. That is a mesh that has an angle of, what is it? 90 minus 87, that's 3 degrees. He's fairly thin. But I mean, if this is just one cell in one unimportant region in your domain, he may still run. So although the check fails, it can still be okay. So don't take it personal when he says fail, you are stupid. He doesn't really mean it. Okay? Skewness, 2.5, that's okay. Something like that. So yeah, there are some cases here where they have played around with some non-orthogonal cells, and yes, you get them as green spheres here. It's possible to view it like that, and also unused points, some yellow spheres, so you see where they are. It's actually possible. Yeah. Doing block mesh, fair enough. That is something you have done already. But we are also now going to use block mesh to create a background mesh for what's called snappy hex mesh. The snappy hex mesh, that is a more advanced, more advanced tool to create or describe more complex geometries, more than the block mesh can handle. So the block mesh alone, yes, it's nice, structured systems. You can have curves, you can have splines, you can have a lot of things. We're going to play a little bit with that in the next exercise. So yeah, you can push only so and so far with block mesh. But when the geometry becomes complex, we have something called snappy hex mesh. So if we have a look at snappy hex mesh, you can find a lot of this. Snappy hex mesh. So here you have snappy hex mesh images, and yeah, this is a nice principle sketch. Flow around the car, and how he then resolves, say, the bad or complex geometry using finer and finer rectangular cells. And yeah, we might have some curved surfaces here on the interface in the end. This one is actually inside the user guide, if I recall correctly. We can have a look at it afterwards. So you have plenty of examples how to use this snappy hex mesh idea. So the point is, you are sort of using a uniform mesh initially from block mesh, and then, given the geometry, tell him to resolve close to the boundaries better and better until you are, say, satisfied to really resolve complex geometries nicely. I think we had, let's see now, this user guide here. Where are we? User guide. Here we are. So inside the user guide, yeah, you see you have this example with this car. Then how to get a good mesh around this complex geometry. Well, you need an STL surface. STL, sort of a file format that is not just an image, but also some logical vector graphics. So you need such an image first, and then smack it onto the background mesh, and then you have several steps to finally end up with a good mesh. So it's several stages here within this snappy hex mesh that has to be performed. You have the possibility here to have a sort of a setup for a snappy hex mesh, a recipe, and then it's done for you automatically. But it's complex. And setting it up yourself, that is not for amateurs. You have some 20 different parameters or something that you can play around with here. So, and the result may be actually fatal. So you can end up with a very bad mesh unless you know what you're doing. So several steps has to be done before you end up with a fine, nice mesh, something like this. You can even add layers close to the surface here if you are interested in really resolving the boundary layers. So the recipe described here is quite short, and we need some better description. So that's actually why I gave you this this PDF file here, meshing in OpenFoam. This one describes the different steps a little bit more thorough. And as an example, they actually have used the logo for this Wolf Dynamics, make a flow around that one. So we can start having a little bit look at it. Let's see now. So you have the background mesh, and then, well, you need a decent background mesh. Not too fine and not too coarse, so that he's capable of describing your geometry. of course, and then step by step how this is done. And trust me, this is quite complex. Also here, for fun, they have the geometry here solid. The flow should go around this object. But here they sort of have created a circle and then told the snappy hex mesh to resolve this circle. But the flow is going to pass right through it anyway. That's also an option. If you really have a region, say, I want to resolve this region in my domain. It's very important. I know I'm going to get high gradients there. I need it to be better than my background mesh. Then you can do stuff like that. So I won't go through this, we don't have time, but you see many steps are needed before you end up with a nice setup. I think I found the style file for this case, if I remember correctly. Let's see. Here we are. Here we have it. So this actually is an STL file of the object that we are going to simulate around. At least for this tutorial they have been playing around with. And the logo looks something like this. Should be the head of a wolf, I guess, something like that. But you see, you have it as a vector graphics in this STL format. And yes, it's going to be three-dimensional. Of course, here we are going to use it as a 2D simulation, so we don't have any three-dimensional variations here. So it's just, just extruded in the set direction. But this is an STL file, or an STL image. It's possible to take any image, take a picture of your head, and then make an STL file of it. And actually you can 3D print it if you want. I guess you're happy with just one head. But then you can have it in 2D and simulate the flow around your head. I mean, your big ears are making a break when you're using bicycles, so you need smaller ears. I mean, you can simulate and test that. So here, a lot of steps needed. I will see if I can find a good setup for you that we can play around with for next exercise. I tried this one, but it was actually not possible to run it because they have changed the names or the different versions of stupid OpenFoam developers. But I got one thing I wanted to show you before we stop. Let's see. Here we had a nice little simulation. The wind around buildings. Let's have a look. So yeah, doesn't look that impressive, does it? But if you flip it around, something is happening here. But this is a full 3D simulation, so not so easy to see what's going on here. Let's look at the mesh only. Solid color. Yeah, still a little bit tricky to see. Say now I remove everything except the wall. Then you see what's going on. So it actually looks like our campus, doesn't it? Main building, and we have some towers. So here you actually have a snappy hex mesh version of, say, some buildings. It's not our campus, but it's close. I think we actually have our campus on a style file somewhere. I think it exists. So yeah, we can do the same. Simulating flow over the entire campus. And if we try to zoom in on one of the buildings here, yeah. It's not that, say, fine mesh for a building. Quite crude mesh, actually. I mean, you have several meters here for a building, for the top of the tower, and you don't have many cells, so quite crude. But I mean, this is a full 3D simulation, so it's rather heavy. But yeah, stuff like that is actually possible. And now I can have a look at, say, the pressure. What's the pressure on these different buildings from the wind? Okay, so obviously the wind is coming from this direction, I guess. What is it on the other side? Not that big. So the snappy hex mesh tool is actually quite powerful. Open many doors, but it's tricky to use. So we will use it carefully, at least in the beginning. Okay, that was a little science fiction, things to come. Any questions? Yeah, then we take lunch.